So basically, it's very easy to write the it's very easy to extend the 1D formulas to 2Ds. To extend the 1D formulas to 2D, we just need to use apply the definition of partial derivative. Basically. So what's the definition? The definition is that a partial derivative with respect to x, for example, is basically a variation in x but holding y constant. So that's just, it's very y, our coordinate y, constant. So we just apply this by first building a 2D grid defined by the points x, suppose xi, every value of xi is equal to some starting point x0 plus I times delta x, and then every point in the y direction is equal to some starting point y0 plus another index, call it j, times delta y. So now we have this grid, which is a two-dimensional grid where we have I for the x direction and j for the y direction. So now we define our function of as a shorthand, this function of two variables, x and y. We're going to use uij to be u of xi comma yj, and apply the finite difference formulas on either variable x and y, acting separately on the indices I and j. It seems logical. So for example, for point I plus 1, comma j plus 1, we do, a Taylor series expansion in 2D. And we can write u I plus 1, comma j plus 1. It's going to be equal to u I j plus the variations. So let's write delta x times d dx plus delta y times d dy applied to, so this is in operator form, applied to the function u at the point ij, plus we need the second order derivatives, and the two-dimensional Taylor expansion is going to give us the same operator, delta x d dx plus delta y d dy squared, acting on u at the point ij, and so on. The third order term is going to have the same operator, delta x d dx plus delta y d dy, but cubed this time, and so on, higher order terms. So you can see how we can construct a first order formula. So for example, the first order fd in the x direction is going to be du dx at ij. It's going to be u at, so we vary only I because it's in a function of x, so let's vary only I in its first order. So we're going to look at, let's look at the forward one, so it's I plus 1 and I, but j stays constant, so I plus 1 comma j minus ui comma j, and this divided by, well, we're varying only x, so delta x, And you can see that this is the first order, so we have an error of order delta x. Similarly, for the y direction, in the y direction we'll have the u dy, and we're going to keep I constant and change j from between j plus 1 and j. The index j is the only one that's going to change there. Follow? Yes, good. And so we can do similarly the backward difference and central difference. For example, let's see, a central difference in x. Central difference in x would be, okay, du dx in I comma j, and we want a central difference, but we only change j. So only the first index changes, and it's central, so we look at I plus 1 and I minus 1, comma j. J doesn't change. Divided by 2 delta x this time, and the order is delta x squared, and so on. It's quite obvious. Okay, so now we have all the ingredients that we need. We can find a second order difference formula, so let's write that one down, so just in case. The second order the CD formula for the second derivative, we're going to use that one too. So it's a central difference, and we have u I plus 1 comma j minus 2u ij plus ui minus 1 comma j divided by delta x squared plus order delta x squared. And in the case of du dy, then I will stay the same, and the variation would be only in the index j. So that you can see how you reconstruct all of these. So we have now all the ingredients to do our next few steps, five onwards. So let's look at those. Step number 5 is going to be 2D linear convection. So for 2D linear convection, we're going to discretize x with the index I, and we're going to discretize y with the index j. So let's see. Let's still do a forward difference in time. So we have un plus 1 minus un. These both guys are at point ij divided by delta t equal to, and we have, notice this is linear convection, so this velocity here is a constant. So let me just write it in the same form as the equation, plus c, and we the du dx. So at the time n, we only change the first index, so let's use, sorry, yes, thank you. So the first index, ij, and at the same time, n, we have I minus 1 and j for a backward difference here, plus c, un, and ij again, minus ij minus 1. And delta y here equal to 0. So we can transpose this to get our only unknown for this explicit method. Now we know it's called explicit. U at n plus 1 ij is equal to un ij. And let's get my signs right. ij minus I minus 1 comma j delta t over delta x, and now we change the j index, and we have a transposed form, explicit. So you're going to do this with the following initial condition. Your initial condition is going to be u equal to 2 at the square domain with x between 0.5 and 1, and also y between 0.5 and 1. Then u is going to be equal to 1 everywhere else, but we're only looking at the domain 0, 2 times 0, 2. Your boundary conditions are u equal to 0 at x equals 0, 2 and y equals 0, 2. So basically this looks like you have a little square like a building. It looks like a, okay, something like a little tower, just that, just a square thing. Okay, so okay, good. Yeah, question? Yes, exactly. Along, not the edges of the buildings, not the edges of the square of the block, say. Yeah. So along here, right? With x equals 0, y equals 0, and 2, and 2. So along that line. All right, we got that. So now let's look quickly at the pseudocode for this. Similar to before, we have our setup where we establish our numerical parameters. Now we have delta x and delta y that we have to compute, and we have nested loops between the two coordinates to fill up the values of our initial condition, which are now defined on a two-dimensional domain. So it's like a 2D structure or something like that. It could be, you could use a matrix of sorts if you want, or just a structure with two. It's like a matrix, ij, with ij as index. And so it's that's our setup. You can see I'm going along x. For each value of x, I'm running along y, and so I'm filling all my values of that square domain with the initial condition. Then down here we have our finite difference approximation written down in Matlab language, right? The same thing that we've written before is right here. It's very simple. That's it. That's the code. Okay. So now 2D convection. The only difference with the previous case is that we don't have a constant velocity. Now we have a velocity, which is u comma v, a vector velocity in 2D space. So now we have two differential equations. So we have a system of differential equations, and we have to write two finite difference formulas. Now this is going to be a bit of a challenge. Let me see, just to write, because it's a lot of writing. Let's just make sure that you all understand how this is written. I might actually skip some steps afterwards. So the time derivative in time, the time derivative of the first coordinate un plus 1 minus un at the same point I comma j, and divided. So by the end of this, you're going to be writing finite difference formulas automatically, plus u at n ij multiplied by du dx. So here we have un ij minus un and x. So we're only changing the first index, I minus 1 comma j divided by delta x, plus v n ij, and it's still u in the derivative, un ij, but we change the second index now, ij minus 1 divided by delta y. Second equation refers to v, so we have vij n plus 1 minus v at time n. Don't give up. We're almost there. un ij, un, not v, it's v here, the derivative of v, n ij minus v n I minus 1 comma j delta x, v again here, v n I j minus v n I j minus 1 delta y. My hand is tired. I don't want to write the transposed form. You see that, I think you can do that, right? That's step 6. So let's look more importantly now at the pseudocode for this. Anybody writing still? Okay. Pseudocode. First, we've got our setup. Again, we have a two-dimensional domain, so we have to do a nested loop to fill out our initial condition on this two-dimensional domain. And we run along x and we run along y, and here we're filling our so if uij is such that x is between 0 and 1 and y is between 0 and 1, then we fill it with a 2. Otherwise, we fill it with a 1. So this is a mistake right here. This should be a v. You can see that this should be a v. Okay, and here we do our finite difference calculation, and we have 3 nested loops. The outer loop is running along time. The inner loops are running along our x direction and our y direction. So we're filling this matrix and then going the next step and filling this matrix, and that's the way we're filling up our values. Okay? A lot of hard work, but it's done in the computer so we don't see it. We just write this and the computer goes and can do 9,000 steps if Casey punches in the numerical parameters. Okay, any questions? Number 6. So 2 more, just 2 more. Hang in there. We're almost there. We'll just look at the 2 more and we're done for the day, okay? 2D diffusion. So this is our step 7. Here's mine. Okay, so we can do this. Let's discretize first. We take our time derivative, un plus 1, I comma j. I bet now you already are thinking this is becoming very easy now to write all of these formulas. So we're going to do first our second derivative in space with respect to x. So we're going to do a central difference, a second order central difference for the second derivative. Okay, so we got u. Everything is going to be in time n, but we're changing the first index between I minus 1 comma j, it's going to be a 2ij, and it's going to be a I plus 1 comma j, all at time n, divided by delta x squared. And the second term now varies on the second index, so we have u I j plus, minus 1, minus 2, u I j plus u I j plus 1, and all is at time n divided by delta y squared. Did I get that right? These are new? Okay. And we can transpose this by multiplying over by delta t and then adding this guy on the other side. So you can see, very easy, we don't need to write this again. Multiply over by delta t, so we're going to have our coefficient is going to be nu delta t over delta x squared, and then we bring this guy to the other side, and that's it. So you're going to use basically the same exact initial condition as before. And the same boundary condition as before. And our pseudocode looks like this. The setup, again, you see how you're going to be reusing for each step, you're going to at least reuse half of the previous one in here. And all you have to change is going to be this little part here, where you have your, actually this, you can copy the text from when you did the 1D case, copy it over, paste it here, copy it twice and change, and make sure that you have your u's and v's. Your derivative with respect to x here and the derivative with respect to y. So it's not really u's and v's, sorry, but that is actually the variation of u with x and with y, which means that u is an index, it has two indices. This one only has one equation. The next one, which is going to be step number 8, we'll have two equations, and now we're putting everything together. We got convection, diffusion in 2D. Now we're putting everything together that we've done until now into a more significant problem, which is Berger's equation in 2D, in 2 dimensions. Very classic problem. And just writing the discretized form is going to get me tired, but I'm just going to write the first part, not the... Yes? V is, so now our unknown function is a vector function u comma v of x and y. This is our unknown. We have two unknowns. So in this case, we have a vector function of space, two-dimensional space. In the 7th step, notice we only have u. So u here is u of x comma y. So it's still two-dimensional, but we only have one unknown. In the next step, it's two-dimensional, but we have two unknowns, u and v. And they're coupled by these two equations. It's a vector field of two independent variables. So, and they're coupled, so we need to write we need to solve them together. You see now why we wanted you to go step by step, because if I just put you if I just put this big guy in front of you, it's going to be quite challenging to make sure that you've got everything, you understand every single term. By starting like we did, gradually you need to understand each element separately. When you get to this point, all of the terms make sense to you, even though it's a big when we write the discretized form, as you will see, it's a big thing. But every term should make sense to you now. We have the first equation. We're going to have two equations, right? We have two differential equations, and so we have to have two finite difference equations. So let's write the one for u. This is the equation for the guy called the first coordinate. So this is going to be our first equation, and this is going to be our second equation. And partial derivative with respect to time. So we have u at n plus 1 and u at n, but at the same point in the grid, so ij, divided by delta t. Then we have plus u at time n, ij, and our finite difference approximation of the u dx. Let's use a backward, a one-sided difference. So we have I comma j minus I minus 1. We're changing the values in j, so I minus 1 comma j, and at the same time delta x plus v n ij u n ij minus u n ij minus 1 delta y equal to new times. We have our two central difference formulas for the second order derivative. Let's write u. It's going to be all are going to be at the time n, but I have both sides of point I. So I plus 1 comma j minus 2 ij plus I minus 1 comma j, all at time n. Second order guy has delta x squared plus u changes now with respect to x. So y, we're doing this term now. U I j minus 1 minus 2 u I j plus u I j plus 1, all at time n, divided by delta y squared. We got our first equation. Every term makes sense to you. Can you write the second equation on your own? What are we going to do? We're just going to put v here, v here. This doesn't change because we had uv and those terms. This doesn't change, but this one's going to be v. This is still going to be the same v, but v here, v there, with all the same indices. And the transposed form, well, we just want to isolate this only unknown for the first equation, this. For the second equation, we're going to have our only unknown is going to be v at n plus 1 ij, and we can isolate that by multiplying by t and moving everything to the other side, and we have our second equation. And our initial conditions and boundary conditions are going to be the same as step 7. So again, you can reuse part of your code, just copy paste that part, and you just need to worry about writing your difference formulas for that part. I think the challenge here is going to be the plotting. We're going to have to scratch our heads a little bit and struggle a little bit to find the right way to present our results here. And it's always like that in computational fluid mechanics. Just when you think you're done, you have a lot more work to do. You're getting the right answer, and you're just halfway there, because now you need to actually visualize your answer. Not only for presentation purposes, to write a paper, to present in a conference, or make a poster or whatever, but also for yourself to understand the solution. The only way to understand the solution is to plot it, to look at it from different angles, to find ways of geometrically represent the data. Okay, so those are the 8 steps. that you should have programmed and experiment with the numerical parameters, discover some things, how the numerical scheme behaves for these initial conditions, and if you have time to try anything else that you want to try, feel free. And you have to prepare a presentation of what you discovered or your experience for Tuesday, the 2nd of February. Only 20 slides, no more. And you should plan to go through them like this, 20 seconds each.